Speaker is Arun Kumar from another representative of Ohio State University, very well represented. We look forward to the talk on sequential calibration of computer models.
Well, good afternoon. This is part of my PhD thesis, which I have submitted 3 days ago. Thank you. And I finished this PhD under guidance of my advisor, Dr. William Knotts. So I'm going to introduce computer experiment in general. We'll talk about the calibration problem for which we are proposing solution. We'll talk about the new method we are proposing for calibration. And then we'll discuss some sequential designs which we have developed specifically to solve the calibration problem. Talk about simulation results, and then we'll conclude with some remarks and future work. If you have any questions, feel free to stop me in between. So we all know we run experiments to collect data, which are then used to learn about the physical system we are investigating. And a physical experiment measures stochastic response corresponding to a set of treatment variables. However, some of the physical experiments are very costly. For example, car crash test, or some physical experiments are infeasible, like cosmology. And if we have mathematical model which can describe this physical system to a good degree of accuracy, then we can solve it numerically using computer programs, which are also known as simulators. And when we run simulator at different input points, that is known as computer experiment. The computer experiments we are dealing with are the time consuming ones. A single run may take several minutes, even days. And because of that, we do not have sufficient data to learn about the physical system we are investigating. And that's where statistics comes into picture. We use statistical models to approximate the response surface from computer experiment. So now I'll talk about calibration. What is calibration? There are two flavors of it. First one is tuning. Say we have this. This is data from a physical system. So x is the input and y is the corresponding output. And then we have a computer model which mimics this physical system, which takes this xc and theta c as input, and yc is the corresponding output. Now x is present in both physical system and computer model, but theta is just an artifact of the mathematical model implemented in the computer program. In tuning, we are trying to find a value for theta c so that next time we run computer experiment, we fix theta c at that value, and we hope that we expect that this, if xp and xc are same, then yp and yc will also be same. So that's tuning. Second is it's known as calibration, where theta is actually present in the physical system and takes a particular value. It's just that we don't know that. Okay. However, the way we approach both this problem in the same fashion. We try to find a value for theta c so that yp and yc are same if xp and xc are same. And if I have time, I'll talk about it why we do that. This notation, when I say physical input, I mean x's. When I say calibration input or parameter, I'm talking about thetas. Example of tuning parameter: mesh size density for a finite element model. Example of calibration parameter: rate of transfer of chemicals through blood. It's a constant, it's there, but we don't know it. And there are several papers where methods have been proposed to solve this kind of problem. The ones I have highlighted here are the ones I'm going to compare with. Okay. All these methods assume that we will have observations from physical experiment. We're going to run computer experiment, we'll have data from there, and we're going to use that to estimate calibration parameter. They do not include a probability of, they do not include the possibility of sequential experimentation. And that's what we all have a question, why a new method? The number of observations we can take is limited, and hence we have to select them wisely. Space filling designs have been popular for computer experiment and hence for calibration, but they may not always be the best choice. If we can run a sequential or multi-stage experiment, then knowledge acquired from the previous steps can be used to decide where we want to run the next computer experiment. And hence we propose a new method to solve calibration problem which allows sequential experimentation. At the same time, we are proposing sequential designs which go along very well with this new method. So what's this new method? We have a data set from physical experiment, data set from computer experiment. We're going to use this data to approximate the response surface for the physical experiment, and we're going to use this data to approximate response surface from computer experiment. And let's say the approximated response surface for the physical experiment looks like this, shown by the dark continuous line. For the computer experiment, we'll have the response surface in 3 dimensions. So we have x, y, and theta. Okay. And what we're going to do is we're going to cut that response surface across the theta axis and project it on x, y axis. And say for different values of theta, this is how the curves look like. And our goal is to find a value of theta so that these dotted lines and this dark continuous line, they are very close. We use the model for the computer experiment response looks like this. This is a constant regression parameter, and this is a zero mean Gaussian stochastic process with power exponential correlation function with power set to 2, if you know what that means. Model for physical experiment looks similar. We have a regression term here, regression parameter, then a zero mean Gaussian stochastic process, then a measurement error term which we assume to be normally distributed with zero mean and a constant variance. Okay. Once we have estimated the parameters for the model, how do we find out how close these 2 curves are that I have shown before? So this is the measure of discrepancy we use. So this is approximated response from the physical experiment. For a fixed value of theta, this is approximated response from computer experiment. And then we integrate it over the domain of physical input. Okay. And theta, which minimizes this expression, is taken as the estimate of calibration parameter. So I just talked about the method for calibration. Now I'll talk about sequential designs. The first criteria we use, I call it maximum uncertainty in prediction. If you look at this discrepancy function, let's assume that we are not going to change this. Okay, so this is fixed. So number of observations from physical experiments is fixed. We have approximated the response surface. Excuse me. It looks good. Then the uncertainty in theta is coming from uncertainty in this YC. Okay. So if we can somehow reduce the uncertainty in this YCs, then we should be able to reduce uncertainty in theta hat. Okay. So what we do is we find a point in the input domain which has the maximum standard error for prediction. Okay? And if we take our new observation at that point, we hope that that will reduce the uncertainty in the approximation for the responses from computer experiment. It turns out that if you look in the entire domain, it's not very efficient. So what we do is we actually fix theta at the estimate we have at the current stage. So the algorithm goes like this. You obtain training data for a reasonable number of design points. You estimate the calibration parameter. If the estimate is good, we are fine. Otherwise, fix calibration parameter at this estimate. In the domain of physical input, you find the point with maximum uncertainty in prediction. Okay? Theta is fixed at its estimate. And this is how you can calculate the standard error for prediction. I'm not going to go into detail of that, but there is a formula which can do that for you. And observe the code at this new design point. So that's the first criteria. The second one is, so the first criteria tries to improve the approximated response surface from computer experiment. But we know that our goal is to get closer to this dark continuous line. Okay? So we look at the difference between these two curves and multiply that to the standard error. And instead of just finding a point with maximum standard error, we find a point which maximizes this expression. Okay? So on one hand, we are trying to improve the response surface. On the other hand, we are also trying to move it towards the approximated response surface from physical experiment. So that's the second criteria. Okay, I'll show you simulation result, then you will believe me. I'm going to compare my method with 3 other methods. These two, NLS method and MLE method, were proposed in this paper by Park and others. And then I'm going to compare it with the Bayesian method proposed by Higdon and others. For these 3 methods, I will have a fixed point design at each step. With our method, we'll have the 2 sequential designs. And it turns out that this NLS method can also be combined with the first criteria. Okay, so that's another method. So there are 6 of them overall. I'm going to plot relative error in the estimate against the total number of observations from computer experiment. And the training data for the physical experiment is going to be fixed. Okay. Another way, we'll have a function. We'll use that function to generate the data. Okay. And this physical experiment data is going to be fixed. We'll have initial set of observations from the computer experiment. Okay. And then we're going to add points sequentially. Now for the three other methods, at each step, we're going to have a new maximum latent hypercube design. I'm going to evaluate the function and use that to estimate the parameter. Okay, so the first example, this is the test function. The true value. This is what we use for the computer model. This is what we use for the physical model. True value for theta is 0.7143. We start with 11-point maximum latent hypercube design. For the physical experiment, we evaluate this function at those points, and that works as the training data from the physical experiment. We do the same thing for the computer experiment, but only with 6 points, and we're going to augment this data set using our 2 criteria. And then I also add normal error generated from random error generated from a normal 0 and standard deviation equal to 0.01. So what you see on the left side, this green line is the second criteria combined with our method. First criteria, this blue line is the first criteria combined with our method, and then this red line is the NLS method proposed by Park and others combined with our method. And we start with 11 observations and we keep adding points, and what this shows is the relative error in the estimate we obtained at each step. On this side we have the Bayesian method, NLS method, and MLE method combined with a fixed point design. And what we see is that the sequential methods seems to have converged, okay, all of them, not the case for the fixed point designs. The second example is a 6-dimensional example with 4 physical input, x1, x2, x3, and x4, and we have 2 calibration input, theta 1 and theta 2. True value for theta 1 and theta 2 is 2 and 4 respectively. Starting design for physical experiment at 20 points, okay, and for the computer 15 points. And here we added random errors generated from normal 0 and sigma equal to 0.1. So this is convergence of estimate for the first parameter. As we can see, for the sequential designs, it seems to have converged. So ideally, it should be parallel to this 0 line. On the other hand, for the fixed point designs, it still seems to be jumping around. For the fixed point design, they do converge after around 60 or 65 observations. So that is for the first parameter. For the second one, the method which combines the first criteria and the method we proposed did not converge. It actually diverged in this case and never came back. However, the method which combines the new method for calibration and the second criteria for sequential designs, that did converge for this parameter. Okay. The NLS method also seems to be doing okay, but hasn't converged after 55 observations. And this is where actually I got stuck in my PhD, and it took me several months to come up with this criteria. And when it converged, I was of course very happy. I closed the door and window just to be nice to neighbors. Now I'll talk about confounding. As I said before, that we do not intend to solve the calibration problem trying to estimate the true value of the calibration parameter. The reason is most of these computer models are actually not perfect. Okay. There is a discrepancy between the response you will get from the physical system and response you get from the computer model. So first thing we have to do is we have to estimate the discrepancy. And if you have estimated the discrepancy well, then you will hope that you will be able to get you'll be able to get the true value of the calibration parameter, which is very difficult because we do not know what is the true discrepancy. Okay. So my method finds one discrepancy and a corresponding estimate of calibration parameter. Some other method may find other discrepancy and some other value of calibration parameter, and we don't know which one is true. So it's not a well posed problem, and that is something that has been discussed in the literature. So in my PhD, I discovered something else. If you have more than more than one calibration parameter. Like in this example is taken from paper by Park and others, which was published in 2001. There are 3 calibration parameters: theta 1, theta 2, and theta 3. Okay. It turns out that there is a very strong dependency between theta 1 and theta 3. In fact, there are multiple different values of theta 1 and theta 3 which does equally well. Okay. And I have a plot for you. This is what I did was I fixed the second parameter theta 2 at its true value, which is 4. Okay. And I plotted discrepancy function that I showed you before for theta 1 and theta 3. Okay. And you can see that this one is, if you can see, this is 10,779.96, and this one is 10,779.97. These are the discrepancies, and they are so small. Okay. And the same, we discovered the same thing when we used the Bayesian method. The joint posterior seems to be pretty flat. Okay. And that's the reason why, in my opinion, tuning seems to be more well-posed problem than calibration, than trying to find the true value of calibration parameter. And that's the reason why we did not attempt to, we do not claim that we can estimate the true value of the calibration parameter. Well, I think I'm going to finish early here. The conclusion is, well, if we can run a sequential method, then we think that the method which combines our new method for calibration and the second criteria seems it's doing better than the other one-step methods. If you are running, if you're not running a sequential experiment, then our simulation study suggests that the Bayesian method seems to do much better than all the other methods. And the future work, currently the sequential designs, they choose one point at a time. What if I'm interested in a batch of points? What if I'm interested in more than one point? And of course, there are a lot of other things that can be done, but I haven't put that here. Okay, I think that's all I have.
If you look at the way Kennedy O'Hagan do this, they model the discrepancy as a function across the input space. Would your design carry over to that sort of structure?
I'm not sure.
Because that seems a much more sophisticated way of handling discrepancy rather than just minimizing the square difference. I just wonder whether you could build a criterion that would take that into account.
Well, at this point, we didn't check that, but yeah, that is something something can be done maybe in the future.
Now, Peter. So you mentioned about confounding issue. I'm wondering, this confounding the global sense or local sense? Global sense basically means for the global whole space, actually there is one unique solution. The local sense basically means although you have a unique global solution, but you have quite a few the local solutions which are pretty similar. So is the confounding due to the global one or the local one?
I'm sorry, I did not understand your question.
So you mentioned there's a confounding issue. For example, you have 3 calibration parameters, theta 1, theta 2, theta 3. The global sense basically means there's no unique solution globally for theta 1, theta 2, and theta 3. It's global sense. The second one is locally. There's no unique theta 1, theta 2, and theta 3.
No, I'm talking globally.
Globally.
Yeah. So there is, what I'm saying is there are multiple different values of this theta 1, theta 2, and theta 3, which gives the same discrepancy.
Exactly the same. Global need to be
Yeah.
exactly the same.
Very close.
Any other comments? Now, I have a comment on what Peter said. I mean, in a way, what you use for sequential design may not necessarily, might be cheaper than what you use for full analysis of the discrepancy. So maybe, Peter was saying that this is a less sophisticated approach, but in design one uses less sophistication. Perhaps anything else, except what Peter said there. Thoughts on this with this week.
I mean, if I could come back, because I've been thinking more about the problem. I mean, when you work out your discrepancy, your computer model and your physical model are actually the same. They're the same functional form, so you should be able to get to a perfect result. If you tried your...
We tried that.
In your simulation, if you made them slightly different, so it could never get to the right answer, then you need to start to model that discrepancy. Did you try that?
Yeah. Yeah.
And
And the performance were, well, we didn't try it in many examples, but there was one example given in the manual for the Bayesian method. It is a software GPMSA. And we tried that example, and the method seems to do okay in that case as well.
I mean, there's a general issue. If I could just comment that you might be using this class of interpolators, but the true function, I mean, put it technically, it may not be in the reproducing kernel Hilbert space in which the emulator works, and there's a question about how far away from the space of functions you're fitting is the actual truth, which is the sort of thing you're talking about, where the same functional form, then it's going to be easier, I think is what he was saying. It could be a different functional class completely. Any other remarks? Well, we'll save us a bit of time. Thanks very much.